Now let's look at phasor in circuits. How does the phasor is used in circuits? First, let's look at resistor. So what do we have here is we have resistor. R. And the input voltage here is VT. And current going through the resistor is IT. Now, if the VT is given, so if we know that VT here is equal to Vm, the amplitude of it, and e to the j omega t plus some phase angle, then we can safely assume the current would have a form of I amplitude Im times e to the j omega t plus theta I. We don't know what it is. We want to figure that out. So by knowing how much voltage is applied to the resistor, and we wanted to know what current it is, all we need to do is apply Ohm's law. So V is equal to Vt is equal to I times R. Now you can see from the, if we use the phasor expression, we have a Vm e to the j theta v is equal to R times Im e to the j theta I. Remember, they both carries e to the j omega t, but this is not giving us any useful information, so we just kick it out, right? Let's just go away. It's the same factor here on both sides. We divide it, and this disappears. So we're really just comparing the amplitude and phase angle. And here's amplitude on this side, and here's amplitude on this side here. And therefore, you can see we know that Im must be equal to Vm divided by R. So we find the magnitude. Now if you look at the phase here, the phase is e to the j theta v. On this side here, we have e to the j theta v. And you can conclude that theta v equals theta I. And you can see then the I, the phasor, the current going through the resistor is just equal to Im. Phase angle is theta I. And we end up with it just Vm over R. And phase angle is theta v. So we find the current. And we can analyze it, the result, and think about it. What is the characteristic of that relationship? That we noticed they both have the same theta, same phase angle. So what do we call this? We call theta I and equals theta v, they're in phase. Now, they're in phase. We can express that in time domain and frequency domain. Frequency domain is in the phasor diagram. So here I have the real part, and this is the imaginary part here. The way the phasor works is really like a vector. It has amplitude, it has a phase angle. And this, if this is Vm, the V. This is V, that's the phasor. The length represents the magnitude, and this is the phase angle, theta V. See, for the current, it's Vm divided by R. We can't compare the amplitude, but they have the same phase angle. So if I draw, I will draw it right here. And this is Im, that's the length of it. But the angle is theta I, and that's equal to theta V. And this is what we call it in phase. You can see they lined up. In the time domain, what does it mean? It means that for the voltage, this is voltage by the way, for the voltage here, if I have theta V, like this. This is the theta V. And this is the voltage. My I is going to be like that. That's called in phase. It's slightly synchronized. They all go to reach to their maximum at the same time. They go down to 0 at the same time. Then they all go reach the maximum, negative side of net maximum same time. Then they all go back to 0 at the same time. They have same phase angle. We call their in phase. That's for the resistor. And that's a very important characteristic. It doesn't matter in how complex circuits, when you look at the connections, voltage across a resistor is always in phase with the current going through the resistor. That we need to remember. So here's an example. We want to calculate the current in a 6 ohm resistor if voltage input is 12 volts times cosine 370 times t minus 30 degrees of volts. As we just obtained the relationship that we know the I, the current I, am is equal to Vm divided by R, which is simply just equal to, Vm is 12 divided by 6, which is 2 now, ampere. Now the phase angle, we remember theta I is equal to theta V, which is equal to negative 30 degrees as well. And therefore, the I can be written, the current in phasor form is just equal to 2 negative 30 degrees ampere. And by the way, the voltage in phasor form is 12 negative 30. In time domain, the IT is equal to the amplitude, which is 2, times cosine omega t, and the omega given is 370 and minus that same phase angle of ampere. So both of these are solution. It's just in a different form. Now let's look at inductor. An inductor, so we have inductor here, and we apply voltage Vt, and we have current going through inductor. We wish to establish the relationship between the voltage and current. So the same thing here, the Vt is given, that is Vm cosine omega t, and certain phase angle. We don't know what it is. Oh, we're given this phase angle. We express that in terms of that theta v, whenever that is. And we assume, again, as we work it out from the RL circuits, the IT has a form of amplitude and also cosine function that has its own phase angle. So we wish to figure out what is the amplitude, what is the phase angle. Now, what we need to start with is the relation that, what is the relation between V and I? And we remember the voltage is equal to L di dt. That end up with that Vm e to the j theta v is equal to j omega L e to the times the amplitude and e to the j theta I. Again, we ignore the e to the j omega t on both sides, or we cancel it out. And here we need to realize something. We feel well, that's a little different now. This amplitude, but our trouble thing here is that this amplitude, but what are we going to do with that one? So here what we need is that we need to remember something. We need to remember from the Euler's equation that e to the j x is equal to cosine x plus j sine x. Now what we are dealing with here is that thing is this j. So this is equal to j. And that means we wanted to know what x has to be equal to in order to have a j. Now, if this is equal to j, that means this one has to be equal to 1, and this term has to be equal to 0. So clearly, very quickly, that we work out the x has to be equal to 90 degrees. And that means that e to the j to the 90 degrees, the phasor, is equal to the j. And remember, e to the j 90 degrees, this is 90 degrees in terms of phasor. So j is 90 degrees, or e to the j 90. So we're going to combine that j and the e exponential function here. And therefore, we end up with the amplitude here is Im is equal to Vm divided by omega L. But this time, theta I is no longer theta V. Because what we're going to do, or what we actually already did, we proved that J is 90 degrees. So I'm going to put on the side. So let's carry this on. This is equal to omega L Im e to the j theta I plus 90. And therefore, we have the amplitude, which is right here. This is the amplitude relationship. And phase angle theta V is equal to theta I plus 90. So that means the theta V is in lead. Again, we want to express that relationship in both frequency domain and time domain. So in frequency domain here, see voltage here is this. That's the Vm. And this is the phase angle, theta V. Theta I is theta V minus 90 degrees. So theta I has to be 90 degrees lagging V. So this is Im. And this angle here is theta I. And theta I is equal to theta V minus 90. Or theta V minus theta I is equal to, theta V minus theta I is equal to 90 degrees. So they are always perpendicular. They're always perpendicular. They're off by 90 degrees. And the voltage is in lead. In time domain, the voltage here is equal to like this. And the current now is lagging by 90 degrees. So it's starting from this point here. And the difference here is 90 degrees. The difference here is 90 degrees, where theta V is, the voltage is leading current by 90 degrees. So that's the I, where this is a V. So the next thing we wanted to look at is capacitor. We're going to look at how the capacitor works and what's the relationship between the current and voltage. Now this time what we know is that we know the current I is equal to C dV dt. Again, we know the V is equal to Vm cosine omega t plus theta V. Again, this is given. And I is equal to Im cosine omega t plus theta I. Now, once we have that relationship, we can see this is equal to C times dV dt. So we take derivative with respect to t. We're going to end up with j omega. And what's left here would be the Vm, the amplitude, and phase angle, j theta V. On this side here, we have Im and phase angle, e to the j theta I. Again, remember that they both have e to the j omega t. On this side here, e to the j omega t, we just ignored it. And we also figured out that the j is the phase angle 90. So we're going to put this in here. We got the j omega c e to the Vm e to the j theta V plus 90. Now we compare, oops, the j is no longer here. Now we compare the amplitude, the Im here, this right here. So the Im is equal to omega c times Vm. And frequently we do Vm divided by, we want to write down in terms of Ohm's law. So we want to divide, but divided by 1 over omega c. Now, if we compare to the phase angle here, theta I is equal to theta V plus 90. So now this time we know the current leads voltage by 90 degrees. Now, same thing that we want to do is we wanted to look at the frequency domain and phasor diagram. See how what's the relationship here. Now this is still our voltage here. That's our Vm. This is our phase angle theta I V. Theta I this time is 90 degrees off and in lead. So we have I is right here, and this 90 degrees. So this is Im, and this phase here is theta I. In time domain, we have voltage like this. Current now is in lead by 90 degrees. So here would be the maximum when it's 0. That would be already maximum here. So it's going to be like that. This is IT, and the phase difference here is 90, and current is in lead. This is a VT.